Two bodies traveling along the same straight line collide in a perfectly elastic collision. So, what is an elastic collision? Elastic collision is where momentum is conserved. So, momentum is conserved, and kinetic energy is also conserved. So, both kinetic energy and momentum are going to be conserved. So, which statement must be correct? Let's read the first statement, which is that the initial speed of one body will be the same as the final speed of the other body. Now, this statement will not be correct. Because if I take one light body and one, let's think of two balls colliding. One is a big one, and the other one is a small one. Uh, Now, in a perfect elastic collision, kinetic energy will be conserved. So kinetic energy half mv square before collision and after collision, they must be equal. So if I take half mv square initially, and let's say this has a velocity of v and this has a velocity of let's call the other one as this would be v1 and this is v2, and we know v2 is equal to 0 because the body is at rest. So the initial kinetic energy would be half mv square, where v would only be equal to v1. This has mass of m1, so let's take that as m1. This has a mass of m2. So this would be my initial kinetic energy of the system, because this is at rest. So v2 is at rest. So v2 squared would be 0. So kinetic energy would only be equal to the kinetic energy of this object over here. And let's assume that after collision, this big ball starts moving in a particular direction, whereas the smaller one stops. So the smaller one comes, hits the bigger one starts moving, and the smaller one stops. It loses its kinetic energy, transfers it to the other ball. So v2 is now no longer equal to 0, but v1 is 0 because this ball is now at rest. So my expression for the final key would be, it's going to be half m2 v2 squared. Now the two kinetic energies, they are going to be equal for an elastic collision, but the velocities cannot be equal because the masses are not equal. It would be true if the masses are the same, but since the two masses are different, so if you can use some expression, if this one is lighter, this one is bigger, the velocity of the bigger object would be smaller, but the kinetic energy, the formula would give you the same value. And the lighter object would travel faster. The bigger object would travel slower when the kinetic energy moves from one object to the other object. So this statement, the initial speed of one body will be the same as the final speed of the other body, is not really going to be correct because it depends on mass. Kinetic energy depends on mass as well. So it's a relationship between mass and velocity, kinetic energy. So it depends on mass as well, not just on velocity. So mass is also going to play an important role, which is why the two velocities are never going to be exactly the same. There are cases, certain cases where they can be the same, but not if the masses are going to be different. So option A is definitely going to be incorrect. Let's read the other options. The relative speed of approach between the two bodies equals the relative speed of separation. This statement is a fact, and this one is going to be correct, that the relative speed of approach and the relative speed of separation, that is always going to be equal. So there's a complete derivation that I've done in one of the video lectures. You can watch that. It's a very long derivation, but always remember that the relative speed of approach between the two bodies is going to be equal to the relative speed of separation. So relatively, the bodies were approaching. This had a velocity of v1, this had a velocity of v2. So the speed of approach was v1 minus v2, and the speed of separation, it's going to be equal. You might like to try your hands on this derivation. You can take two bodies with velocities u1 and u2, and after collision the two bodies are moving with v1 and v2. So you can use for an elastic collision, the initial momentum is equal to final momentum, and for an elastic collision, the kinetic energy, initial kinetic energy and the final kinetic energies, they are going to be equal. So using these two equations, you can solve them simultaneously and somehow get rid of m1 and m2 both, and in the end you're going to get this. So the relative speed of approach and the relative speed of separation, that's going to be equal for, remember, for an elastic collision. If the collision is inelastic, then this statement is not going to hold true.